And I'm going to go to our home page. I'm going to look at it as a student. Okay, well, I always like to begin by asking, do you have any questions about anything so far?
Not really. I'm not very versed in the physics world.
Yeah. Yeah, that's a thorny topic, I guess, because, you know, there are actually schools, and I've heard that in most European schools, children learn physics first, and they learn it quite early. I mean, like in elementary school, but of course they learn a very simple version of it, not much math. And as they go along, after a few years, they learn a little bit of chemistry, but they don't stop learning physics. They keep learning more advanced physics as they learn some chemistry. And then, when they're advanced enough in chemistry, they start learning biology because, you know, to a lot of educators, and certainly to physicists, learning about, you know, the way it's often done in American schools is, well, you learn, I don't know, maybe you get some natural science, whatever that is. That's a bit of everything. And then when you get maybe in middle school or high school, you learn biology and maybe some chemistry. And then if you're really ambitious, you go out for that really tough course that everyone's afraid of, you know, physics. But that's, to a physicist, that's like building a house from the roof down, because physics is actually the foundation of all those sciences. And I mean, physicists do suffer from, or let me say, they do not suffer from small egos a lot of times. Um, but you know, from a physicist's point of view, it's all physics. It's just that when you get to chemistry, you start looking at systems that are much, you know, actually, physics deals with the nature on its simplest level. The fundamental laws, the elementary particles. If you want to draw an analogy, it's like learning the basic moves of chess. You know, that a pawn can move, you know, forwards 1 or 2 steps, and it can move diagonally to catch another pawn, and a, a knight can go up 2 spaces and 1 over, or up 1 space and 2 over. That's what physics is. You know the pieces and you know the moves. Then chemistry is like the games, the whole game, you know, the whole complicated mess of the game. And biology, now I'm pushing this, I get myself into trouble with analogies, so don't take them too literally. But then biology is like the entire tournament. You know, if you have a chess tournament, you have all these games going on at once. There's no way you can understand everything at the very basic level. You have to look at the bigger picture, more general picture. And that's certainly the case with the sciences. I mean, they're all related. And in a sense, it's all physics. I mean, in principle, you could explain everything by physics. Physics, if you know the rules, then you just play the game and you find out how the world develops. And you have life forms and uh, human beings and personalities, and all that stuff could, in principle, be explained by physics. But that's only in principle. In reality, it's so complex. There's no computers in the world that could do all the mathematics necessary to understand the world at that level. So that's why we kind of break sciences down into, you know, the natural sciences anywhere, physics and chemistry and biology. But they build on one another. So chemistry builds on physics and biology builds on chemistry. Anyway, that's my little sermon. Anyway, have you read the chapter for this week? Have you gotten through that?
I have not yet. I had to go out of town and I just got back today, so I was luckily to do the post, but didn't get a chance to do the
Okay.
reading.
Yeah. So one thing I want to say about this book, it's kind of a weird book to choose. I mean, I didn't choose the book for this course. In a way, it's a poor choice maybe for an introductory physics course. In another way, it's a brilliant choice because one thing Feynman had, if you look him up on YouTube, there's lots of videos. He's a rock star to physicists, okay? Um, he's like to pop musicians, he's like the Beatles or the Rolling Stones or something. Um, he was a very entertaining. I mean, he's a Nobel Prize winning physicist. He helped develop what's called quantum electrodynamics, which is considered the most accurate theory in physics. I mean, they can calculate things to an accuracy of like 12 decimal places using that theory. And he was also a very big personality. He could entertain people. He was very entertaining to listen to. But there's drawbacks to that too. And to illustrate that, I had a professor who actually, I don't know if he attended a course from Feynman or he just attended some lectures, but he went to some lectures by Feynman when Feynman was still alive. Feynman died I'm trying to remember now, in the late 90s, I think, late 1990s. But he attended some lectures. He said the thing about Feynman was you listen to his lecture, and while you're listening to it, you felt like you understood everything. I mean, everything was, I mean, it was so entertaining. You didn't get tired, didn't get bored. And he explained everything with so much energy that you just were carried along on the wave of his, personality. But he said the moment you left that lecture hall and started talking to other people, you realized you didn't know you walked away from that lecture not knowing anything. So, I'm afraid that might be potentially a problem with the textbook as well, that and of course the course is just to kind of introduce you to physics, so you're not expected to go out and solve physics problems as a result of this course. You're just hopefully going to appreciate more what physics is. And in that sense, his book does a very good job. Another thing about the book, though, is that although our edition is, I think it's 2011, that's just, probably minor edits, maybe spelling corrections and grammatical things. There's the content of the lectures that are condensed down in this book, 6 Easy Pieces, come from lectures he did in 1963. And physics has moved on from that time. I mean, 1963, right? That's about 60 years ago. So when he says, I was reviewing the chapter today, chapter 2, and he said something about the strong nuclear force. And I forget exactly what he said, but basically it was that we don't understand anything about it. Well, we do understand that force now. It's called, we have a theory to explain it. It's called quantum chromodynamics, and it's expressed in terms of quarks and gluons, which I don't think he'll mention in this text, in this book, because he was talking about it too early. But on the other hand, physics is in a bit of a bind because it's a victim of its own success. A lot of basically the physics we talk about now, I mean, if you go to a conference, a modern physics conference, they're just looking at the consequences of things that were worked out by the 1970s, or certainly by the 1980s. In fact, one of the more recent Nobel Prizes, the discovery of the Higgs boson, I don't know if you heard about that a few years ago, but that was a big deal. But the Higgs boson was predicted. That's a particle. It's a particle that gives things mass. It explains the existence of mass, which is a great mystery, and I can't even claim to understand it, to be honest. But this particle was predicted in the 1960s by Peter Higgs. That's how it got its name. I hope I got his first name right. I know I got his last name right. But some people they like fancy, or they like evocative names. Like there's a book called The God Particle, and it's about the Higgs boson. And I don't know why they use that term, but I guess it's just so fundamental to everything. They wanted to give it a sexy name, so they called it the God particle. But it's just it's a very important fundamental particle in our understanding of nature. And the thing is, we've discovered all these particles that were predicted, which is an amazing thing. I mean, physicists 50 years ago or 60 years ago made predictions that maybe a decade ago were found to be true. That's pretty incredible. Um, but there haven't been new things discovered. And the thing is, the theory, the standard theory, isn't making more predictions. So it's kind of wrapped up. And physics is always looking for the next big horizon, you know. And it might be right around the corner, but on the other hand, it might be decades or centuries away. Who knows? Before the next big thing comes along. Anyway, I'm just musing. I'm just talking almost nonsense here. While I've been giving my little meandering speech, have any thoughts come to mind? Anything you want to comment on, or not?
Yeah, we pretty much in my family we like a lot of Neil deGrasse Tyson, and we do speak
Yeah.
about space, and we've mentioned the God particle before, but the ironic thing is I just really never thought of it as physics so much as it was just really cool space stuff because of how he presents the material, like you were saying with the other gentleman. It just it's captivating, and then when you go and try to talk to somebody else about it, you're like, well, I knew what he was talking about when I heard him say it, but now I really
Well, see
can't
if
explain
you,
it.
yeah, I mean, if you listen enough to Neil Tyson or read about him, you see that he refers to himself. His title is astrophysicist. He's a physicist who specializes in phenomena in beyond the the Earth. So I mean that is physics. That is physics. Physics is a big topic. So you can be a physicist who studies the nature of uh, materials. That would be like a, we used to call them solid state physicists. Now they're called condensed matter physicists. There's people who study the fundamental particles of nature. They're called high energy physicists. There's people like Neil Tyson who talks about black holes and the expansion of the universe and all these things, and that's an astrophysicist. But they're all physicists who, nowadays physics is such a big. It's like in um, biology. I mean, there's evolutionary biologists, there's molecular biologists, there's all, these are big fields, and there's no way um, that one person can really have a grasp on all the, all the ramifications of these things. It used to be, centuries ago, a person who was a physicist or a biologist or a chemist, what we might call a physicist, biologist, or chemist today, just called themselves a natural scientist. There was no distinction between biology, chemistry, and physics or astronomy. I mean, astronomy nowadays is usually taught in the physics department. I teach also at Purdue University, and we're called the Department of Physics and Astronomy because astronomy is just a branch of physics that specializes in the study of objects, objects beyond the Earth. But explaining those things, they use the same tools as every physicist does. They use conservation of energy, conservation of mass, relativity, quantum mechanics, all these things, which are the basic tools of physics, are used in all these branches. I mean, there's also geophysicists, which are basically geologists who study the structure of the Earth in detail, trying to understand the forces and the actual processes that occur within the Earth. So that's really all physics, and I think that's a thing that maybe is a good thing about Feynman's book, if it kind of brings that forward. I think that physics is fun. It's just basically the study of nature at the most fundamental level. But the thing is, physics tends to be more mathematical than the other sciences because the questions physicists are interested in answering usually are simple enough that we can apply mathematics to them. You know, how are you going to apply mathematics to a mouse? You know, it's you can't model a mouse in all its complexity, and certainly not a human, or even an amoeba, at the detail that a physicist models the behavior of an atom, you know, the electrons and the protons within an atom. So you know, those are problems we can actually solve, and in biology, the systems are much more complex, so we can only apply kind of high-level general rules to things, which is, you know, as we get more, you know, the fields have crossed. I mean, if you go back in the 1950s, it's one of my favorite stories, in fact. It's the story of Watson and Crick and the discovery of DNA, which is one of the most important discoveries of all time. I mean, it's totally transformed medicine, for better or for worse. I mean, you can see it both ways, I suppose. But Francis Crick was a physicist before and during World War II. When the war was over, he was in his mid-30s. He had spent what he felt were his most productive years. You know, if you look at great physicists, most of them, you know, Einstein wrote his 3 greatest papers when he was 25 years old. He was a young guy. And that's true of most physicists. They're, you know, by the time they're in their 30s, they're already old folks. So Crick was in his mid-30s, and he was at Cambridge, and he felt his best years were behind him, that he had no chance, because he had spent the years working for the Department of Defense, or whatever they called it in Great Britain, developing methods of detecting underwater mines, which is a perfect job for a physicist. Physicists, you know, invented all these things. So, but, you know, that's not, for someone like Crick, that was not creative work. He was just applying physics to solve important problems, but problems of defense, not in understanding nature. So he started thinking about what could he do where he could make an impact on science, and he felt that his chance of doing anything big in physics was past. But then he thought, you know, understanding the mind, how the mind works, he thought that was one problem that needed to be solved. But he thought that problem is, if we ever solve it, it's so far in the future, he figured he'd never have a chance to make an impact there. And then he said the nature of the gene. He thought that was a problem that was very important, had not been solved, and that he could solve in his lifetime. And he was right. But he applied his knowledge of physics to understand the structure of DNA. And he used all the tools of physics to do that, X-ray crystallography, all these things. I mean, he didn't work alone. Obviously, he had a partner, Watson, who was more from the biology side. But that's where physics, and that's a great example where physics and biology cross paths. And when they saw the DNA structure, they immediately understood how the cell could replicate. And it also made total sense in light of evolution. Suddenly they understood how mutations work and how natural selection, you know, things that were anticipated by Darwin, but Darwin had no idea. He had you know, he came way too early. It was in the 1800s. He didn't know about the nucleus of the cell, or meiosis and mitosis, and all these things about cell division and chromosomes and all that. But he did understand that there must be some fundamental, for lack of a better term, atom in the nucleus that contained the information that had to be carried on to the next generation. But there had to be errors in the replication, which we call mutations, that allowed creatures to evolve. So when they saw DNA, it was just like opening the windows, you know, they saw the light. It all made sense at that point. Anyway, but all these methods, you know, X-rays, CT scans, MRIs, these are all inventions of physicists that have been adapted for use in other fields. The MRI was originally called a nuclear magnetic NMR, actually, NMR, nuclear magnetic resonance, where MRI stands for magnetic resonance imaging. And they call it MRI because that doesn't sound as scary to people. If you say nuclear, people don't like that term. But it's nuclear, but it's not radioactive. It has nothing to do with radioactivity. In fact, an MRI is much safer than a CT scan. There's no radiation, or at least no dangerous radiation involved there. But the MRI was, or NMR technique was developed to study the behavior of the nucleus and study the magnetic moment of the nucleus. That was nuclear physics. And that was developed by a physicist his last name was Rabi, R-A-B-I, and he invented that back in my dates aren't so good, but I think like the 1950s or so. So he invented that to do physics. And now the MRI is so fundamental to imaging. GPS, we wouldn't have GPS if Einstein in around 1919 hadn't come up with his general theory of relativity, because they have to make corrections to the time signals from those satellites based on where they are in the gravitational field of the Earth and how fast they're moving. If it weren't for Einstein's theory of relativity, GPS wouldn't work. So those guys out on their little boat trying to find their fishing hole using GPS, or people trying to navigate their way to a new restaurant, really have to thank Einstein for that, because that whole thing wouldn't work without Einstein. Of course, Newton too. If it weren't for Newton, we wouldn't understand how to put things in orbit and all those things, all those ideas. So, I don't think a lot of people realize that the role physics plays in everything. The laser was invented by physicists, and it's a totally quantum mechanical device. The transistor was invented by physicists. Without the transistor, we wouldn't be talking on this computer right now. We wouldn't have smartphones. The world would be totally different. And from some points of view, it might have been nicer without these inventions. I don't know. We live in a much higher stress, fast-paced world than people used to live in. So you can argue both ways. But one thing you can't argue about is that physics has totally transformed the world, probably more than any other human discipline. So now, do you have any other questions or comments? The next thing I want to do is I'm just going to go through the simulation. Or did I put you to sleep?
No, I'm ready to go.
Okay. All right. Yeah, so I usually like to do just step through the simulation, and I hope, I get the feeling I'm still grading the first weeks. They're painful, believe me. These essays are murder to grade. But I'm getting through them, and but I've seen many of the essays are very good. So either by luck or people have actually watched my previous videos, they did exactly what I asked for. But then there's some other essays where it looks like not only did students not watch my videos, but I don't think they even read the instructions, because there's very little relationship between the essay and what they were asked to do. So I hope some of those students out there are watching this video. Whoops, we don't need to do the discussion. We want to look here at the summative assessment for week 2. All right. By the way, have you started the assessment? Have you done that yet? Have you looked at
I said, I was out of town, so I wasn't able to start.
Okay.
The good stuff.
Well, that's good in a way. Then this will be beneficial. So, I know from past experience, some students don't know what happens when they click. Either they don't click on this link, or when they click on it, they don't know what's going on. So if you click on the assessment guide, it's very important to open the assessment guide, because it explains what to do. So you click on it, and it doesn't automatically open, at least when I do it in Chrome. but it downloads a file. If you don't see it, if you're using Chrome, I assume it would work the same for just about everyone. It downloads a Word document, and it's right there in the lower left-hand corner of the screen. If you don't see it there, then look in your downloads folder or wherever it goes. If you're a Mac user, you know, things are arranged differently. It's been years since I've used a Mac, so I don't really remember what that is. But, you know, wherever downloads go there, and you should see this document file. Open it up. And I suggest just, well, if you do it on your phone, it's a problem. You might want to read it and take notes. But if you have a bigger screen, you can just split the screen and look at it, and then find the window that you had open. There we go, I think. And then go click the simulation. And it's all spelled out here. It says click phase changes from the home screen. So I've opened the simulation, but I'm going to click phase changes. I've seen some essays where it looked like students did both parts for last week. You know, in the first week's essays, they were doing both of these, and it clearly said to do the first one and to do it for oxygen, and they just did it for everything. And so clearly they weren't reading the instructions. So it's important to follow directions. I can't emphasize that enough. All right, so follow directions. So it says click on phase changes. There, you have to click on it again to open it up, and you see this figure here. Okay, it says from the atoms and molecules, don't always go by the picture. In this case, I think it does agree. From the atoms and molecules menu on the top right, select neon. So we have neon already. Note the shading or note the reading on the thermometer and pressure sensor near the top of the container. I'm not going to say the values, but you see the numbers. Write those numbers down. Put them in your essay. Say that at the beginning, I selected neon, and it was solid, and the temperature was whatever it is, and the pressure was whatever it is. Okay. Arrows even indicated here. Okay, push the lid of the container down so there is less space in the container. Observe and note what happens to the temperature and pressure. So when you're writing this essay, you can say, well, I clicked on the lid and I pushed it down, and I'm not going to tell you what to write, but you see what's happening or what's not happening. You know, you say you push it down a while and whatever happened, happened, or whatever didn't happen, happened. And then, you know, now it gets a little more interesting as I actually get in contact with it and explain what's happening, and maybe give some numbers. I mean, you don't have to give me a lot of detail, but I like to get a few examples of some numbers. Uh-oh, did I lose you? Or did somebody join? Are you still there?
It's Nicole, Professor. I just had a question as you were doing this.
Oh, okay. You raised your hand. All right. What's your question?
No, I mean, you were kind of answering it. So I had started working on this and like just trying to put in numbers. So you're saying it's okay if we do like a couple numbers when they change in pressure and temperature in our essay?
Yes.
Okay.
You know, like I don't want to give you the actual things I want you to would like you to say, but you know, you could say at the beginning when I started pushing the lid down, I saw whatever, and then once the lid contacted the atoms, then something changed and the pressure, you know, increased to some value, and the temperature was whatever it was, right? And then maybe, you know, do one or more examples.
Okay.
You see something that interesting that just happened there, you could report that and what the values of pressure and temperature were at that moment when the lid went off. Okay, so I think we covered this part. You will need to place your mouse, yeah, keep moving the finger until you see changes in the temperature and pressure reading. So, you know, just say what those changes were and give a couple of examples. This says reset the simulation. So in your essay, you could say, after I blew the lid off, I reset the simulation. This says note the reading on, again, write down what you see, and then add more particles to the container. So now we're going to pump more particles in there. And you can just, you know, say I added a bunch of particles, and, you know, what happened? Did pressure change? Temperature change? What's an example of the pressure and temperature I saw? You might want to stop pumping for a moment to let things settle down, and, you know, you see that there's fluctuations, so just kind of give an average value. It doesn't have to be exact. You know, use the pump. You will need to place, well, we did that. You will see additional particles moving in the container. Then it says, you know, so observe that for a while. You might want to pump more in than I did. And then when you're done with that, reset it. Now it wants you to cool the container. Okay, you've done this before in the previous simulation. So I think you're going to see the same thing you saw before. Okay. Continue to cool the sample until the thermometer reaches the lowest possible reading. Observe the lowest possible reading. Pay attention to changes in motion of the molecules. So what do you see happening here or not happening? Note the pressure and temperature. Well, those numbers are pretty easy to read. By the way, I prefer, I mean, if you want to do it in Celsius, that's okay. But, you know, it's by default in Kelvin, and that's actually a more convenient unit in physics. Okay, just, you know, so I don't care which unit you use, but I would prefer that use Kelvin. Continue to, then says, you know, now we've reset it, we're gonna slide it to heat. So we're heating it up. Continue to heat the sample until the thermometer reaches the highest possible reading. Observe the highest reading and pay attention to the change in motion of molecules as you do this. Note the pressure and temperature of the hottest setting. So, you know, just watch it for a while and see how hot you can get it. I'll leave that to you. And that's it, right? I've done the simulation. And, you know, if you basically wrote down the kinds of things I said, and when you run the simulation, write down the corresponding numbers, then you have everything you need for your essay. But look at, when you're writing your essay, look at the rubric as you write it. Do all these things, okay? Describe what was done. So the steps that you performed. What did you observe? How did the molecules or atoms move? What was the temperature and pressure? Just give some examples. I don't expect more than a few sentences, but it might need a few sentences, you know. I'm not going to hold you to this limit. It's hard sometimes to stay within this limit. So don't feel restricted to this. I hope you don't write me a 2,000 word essay, because that's just more for me to read. But you know, 500 words or 750 words, something like that should be enough. But don't be afraid to go over if you have to. Okay. And, you know, you can break down this to see what I'm looking for here. Did you thoroughly describe? If I read, you know, suppose that I just came to this totally fresh. I've never done the simulation. I want you to tell me how to do it, you know, so you would tell me maybe the website to go to and what to click on, you know, and then those steps. You don't have to say a lot of words, but give me enough information so I could kind of follow the recipe, so I could reproduce your results. All right, and then describe what you observe. So that's, you know, that's where you talk about the motion that you observe and what are some examples of temperature and pressure. you know, you might say something like I pumped more argon atoms into it. Wait, what were we doing? Where was it, argon or neon? Now I forget. We were doing, I think we were doing neon, weren't we? Well, if I looked at the instructions, I would know. Looks like neon. Yeah, neon, sorry. So we're doing neon. It's important too. Tell me which atom we're simulating. Some students don't even mention that. Okay. Some additional questions. I know sometimes it's hard to come up with questions, but come up with a question anyway, and make it relevant to what you're reading this week and to the simulation. So, you know, read the chapter and try to relate what you observe in the simulation to a couple of key ideas in the reading assignment. I'm not too critical, I'm not too particular, but if you start talking about black holes or non-locality or things like this, those are physics, those are part of physics, but they're not relevant to this, you know, what we're studying this week. So don't go too much on a tangent. Relate it to what we're actually doing. And then again, what are you learning about atomic motion specifically from this simulation? By the way, these simulations, it simulates the classical physics understanding of atomic motion. So, you know, you saw that when I went to a certain temperature, I won't say what that temperature was, it looked like all motion ceased. But if you read Feynman, he says you never really get the motion to cease completely because of the quantum mechanical effect called the uncertainty principle. But we don't, you know, uncertainty principle, you can mention it, but it is not really relevant to the simulation because I don't think they consider it in the simulation. It's just classical physics, which, by the way, works very, very well for just about everything. I mean, we can send a man to the moon, or a woman, or just about anything to the moon or to Mars or other places based on classical physics. We don't need really any physics after the late 1800s. Everything you need to know was figured out in the 1800s. The rest was, you know, refining our technology, but the fundamental knowledge was there already. Okay. Discuss how the observations relate to the developments in the understanding of atomic motion. Yeah, I already talked about that. Use of references. A lot of students don't list references. At the very minimum, you should be referencing this text, your textbook. So I think I have something open where I show the reference. Here it is right here. Okay. Feynman's book, obviously. So at least cite that. If you look at some other references or if you look at a YouTube video, that's okay. Just give me enough information so I could find it. And then, of course, the mechanics. Try to write in complete sentences. Check your spelling, your punctuation, your grammar. A good thing to do is, these aren't very long essays. Read it out loud to yourself, or even better, if someone's willing to listen, read it to somebody else, a family member or a friend, and just see if it makes sense when you read it out loud. I mean, all of you speak well, so you should be able to write as well as, at least as well as you speak. So if you read it out loud and it comes off the tongue nicely, you should be able to, you should be fine. But a lot of times if you read it out loud, you'll find that maybe you left out a definite article, or you'll notice that you misspelled something, or maybe you need a comma someplace, right? So, and then I really usually don't look at this unless I find a lot of grammatical errors and stuff. I might take a few points off here as well. The use of language. You know, if it's written like a fourth grader, then I might take something off here. If it's at least high school level, I'm not going to touch this one. What else did I want to say? I had something just before I said that. I had something I want. Oh, it helps me a lot when grading. Just realize I'm grading 2 of these courses actually, and each course has like 25 students, and so that's like something like 50 of these essays I have to read through. And I open up the rubric and I go through the rubric as I read it. So I'm spending at least 5 minutes per essay, and I'm looking at 50 essays. You know, that's 250 minutes um, reading essays, and believe me, it could be longer than that as when I get tired. So it makes it very helpful to me if you say something like, like here where it talks about discuss how the observations relate to the developments in the understanding of atomic motion in classical physics. You could say that from my observations, my understanding of atomic motion in classical physics was increased because I realized that such and such occurs, or something like that. Start that discussion out with a phrase that makes it clear that you're talking about this part, this part of the rubric. Too specific, you can have a couple sentences or 3 sentences. It started out by saying a couple specific ideas from the reading that were related to the observations were, and then go into your discussion of that, because that really makes it clear to me that you were addressing that, because sometimes students scatter all those things throughout their essay, and I want to be fair when I read it, but sometimes it's hard for me to tell, have you really done that? I don't want to say you haven't done that, but if it's not clear that you have, then I will take some points off, because I like it to be pretty clear. And another thing, I think this is the last thing I want to say about it. Please, if you want to use Word to write your essay, go ahead and write it in Word. But once it's done, copy the text from Word and just paste it in here. Is it going to let me do that? Oh, I probably need to close the rubric. Let me try it again. Okay. And just paste it in there, and then maybe edit it a little bit. Uploading a Word document, attaching a Word document or a PDF or any other kind of format is a real pain for me to grade, because the way it works, I don't know if I can show you here. Let me try to copy this whole thing in here. It might show better what I'm talking about. Well, I can't really, because I'd have to be in grading mode, and I can't do that because I'm looking at it as a student. But if you try to grade with a rubric, then well, you just saw it actually. I open up the rubric, I want to do something, I'm looking down here, and then I want to edit it and see what happened. Everything collapsed again, or reset. I'm constantly going back and forth. It's a real pain. But if you just paste the text in, then it works much better. Actually, what I just showed was probably not right, because I didn't upload as a Word document. But if it's a Word document, it's a real pain to grade. Take my word for it. So just paste the text in there, please. Okay, I've been saying a lot, and now I'm going to give you the microphone back. You have anything you want to bring up? Oh wait, we have. Okay, Nicole, maybe I've spoken to you already. Yeah, Satina originally was here, and now I guess you joined. I didn't even realize that. So, Satina and/or Nicole, are there any questions?
It's Nicole again, Professor. Just one quick. Just going back to the essay that we have to do. The last bullet point that talks about the observation, it's kind of also just saying about what we learned from the lab and how it relates to the atomic motion and classical physics.
That's right.
Okay.